Okay, so we have talked about the contraction of a protostar. We have talked about its two stages. The first stage, rapid fall stage. Next stage, slow contraction stage, right? And also we have seen how the temperature for our test case increases from 20 Kelvin to 30,000 Kelvin, right? Now the question is, okay, so during the contraction, the system, it remains close to hydrostatic equilibrium and the temperature increases, right? So the question is, you must be wondering, we started from 20 Kelvin and slow contraction started around 30,000 Kelvin, right? So the question is, how much will the temperature rise? So 20 Kelvin keeps on increasing to 30,000 Kelvin, okay? 30,000 Kelvin. So the question is, where will it end? That means we want to now find what is the maximum possible temperature. Right? It will not be mass actually. Here written mass, it will not be mass. It will be temperature. Maximum mass is different, right? And in fact, I will tell you what is the maximum possible mass of a star in that case. And it is also very easy to understand. Maximum possible mass. How? Here we have got, now if you consider a star, inside a star we have got two competing forces, gas pressure and the gravity. Now, maximum possible mass means after that what will happen? The star will explode. Okay, and when does it, how is it possible? When the gas pressure becomes very large. So that way we can estimate the maximum possible mass of a star. I will show you later on. But this is how you estimate. Maximum possible gas pressure which can uphold against gravity, and if it is more, gravity will not be able to uphold the gas pressure. And then just like a balloon, it will blow up. If we blow more air inside a balloon, it just bursts out, the star will again burst out. And that is how we will estimate the maximum possible mass. But that's in some other class. Here we will estimate the maximum possible temperature of a protostar. Okay, so this is the question. So now, how do we do that? The thing is that, as I have been repeatedly telling you, so we have during the contraction, gas pressure versus gravity. Now it can happen that after some time, what will happen is that all the atoms, they are slowly, electrons, protons coming close to each other. Now till now we are having a classical gas, non-relativistic classical gas, right? Why classical? Because the distance between the two electrons or two atoms was much larger than their de Broglie value. Okay, but now there is the possibility, as it keeps on, the system size keeps on decreasing, there is the possibility that two electrons come very close to each other, so that their separation becomes close to their de Broglie wavelength, and then we can no longer consider them as classical gas, because actually they are quantum particles, so it will be a quantum gas. Now what happens? So what will happen is that gravity will try to, now talking about de Broglie wavelength, whose de Broglie wavelength is more? Proton versus electron. Obviously electron. Lambda is equal to h by p mv, right? Whose mass is less? Electron, 2000 times lower. So its de Broglie wavelength will be 2000 times more, right? So I am talking about electrons first. So when they start contracting, it will be the electrons first whose distance will become closer to their de Broglie wavelength and not the protons. Okay, now what will happen? The gravity will try to put all the electrons in the same energy state, or that means in the state with same quantum number, and there gravity goes against the rule. Why? Because electrons are fermions, They follow Pauli's exclusion principle. No two electrons can have the same quantum number. Forget about the same energy state, right? So what will happen? Electrons will immediately say we will not be in a state with the same quantum number. This statement that electrons give, that we will not stay, this statement, this causes a force or a pressure which is degeneracy pressure, right? And this will be now the new opponent of our gravity. Previously gravity's only foe or enemy was the gas pressure, but now it has got a newer enemy, which is the degeneracy pressure of electrons. Remember, degeneracy pressure of electrons. Now what about the gas pressure? Well, it is also there, but in this case now degeneracy pressure is much more than gas pressure. Okay, so now let's see. So we are talking about electrons. What's the de Broglie wavelength of electron? Lambda is equal to h by p or mg. Since we are considering a classical gas having kinetic energies of the order of kBt, so this is the momentum, and our condition for classical gas is distance, inter-separation distance between electrons is much more than their de Broglie wavelength, and this condition can be easily translated into density, mass by lambda dB cube, and this is the relation. Okay. So now what we are going to do next, we are going to use all these ideas. Just previously what we did, we used all these ideas and input it into our Fourier theorem, right? So this is what we will go to do next. Okay, so as I was saying, see Fourier theorem statement for a non-relativistic system in hydrostatic equilibrium. 2 E kinetic energy plus gravitational energy equal to 0, and this is the expression for kinetic energy, and this is that for gravitational energy. Now if we do that, then from here you can equate this temperature. Okay, this is what we want to do. We want to find the temperature, and see here we get kBt is of the order of this expression. Remember here T is proportional to rho to the power 1 by 3. So as the contraction happens, right, what is happening? Density is slowly increasing, and as a result temperature is increasing. They are coming close to each other, see? And remember, this is valid when L is much greater than or even greater than lambda dB, because we now have classical electrons. But when slowly, after some time, during contraction, when the length becomes to that inter-separation distance becomes to that of lambda dB, then we will have degenerate electrons, right? And in that case, what will happen here, you see, in the case for degenerate electrons, we derived this relation previously. So density, now what we will do, we will equate this density over here. We will put this density over here. This expression will be put over there, and then we will find the value of temperature. So this is the temperature. When this temperature, so what is happening during contraction, temperature increases. Now this is the temperature where all the electrons have become degenerate, and now degenerate electrons have started resisting the gravitational contraction. Okay, so in a way, remember what happens in degenerate matter. In degenerate matter, pressure is independent of temperature, unlike the classical, unlike the normal gas. So what will happen after this temperature? All the electrons, they have become degenerate, and so temperature will not rise after this. So this is the maximum possible or maximum temperature of a protostar, where the electrons inside the cloud have become degenerate. Okay. Any questions?